Welcome to a screencast on an introduction to Hess's Law. The objectives of this screencast are to explain Hess's Law and to use Hess's Law to calculate reaction enthalpies. Now, this is usually most easily seen by doing an example. So, in this example, we are given a couple thermochemical equations, forming copper oxide from copper and oxygen, and forming aluminum oxide from aluminum and oxygen. And we're interested in determining the enthalpy change for the reaction of copper oxide with aluminum to make copper and aluminum oxide. And the given thermochemical equations we know the delta H values for. The one we're interested in, we don't know the delta H value for. As a bit of a side note, the equation we're interested in is what's called a thermite reaction. And we're going to try to find the delta H for that in kind of the usual way that we try to solve problems in chemistry. We have some given information. In this case, it's two different thermochemical equations. We're trying to determine something, in this case, the delta H value for a different chemical equation. And we have to find some way to get from what we are given or know to what we'd like to find out. Now, if you notice, these given equations actually have the substances in them that are in the reaction equation of interest, the thermite reaction. So what we're going to do is we're going to take those given equations and then add them up in just the right way to get the equation of interest and therefore the delta H of interest. And to do this, we manipulate the given thermochemical equations by doing things like doubling or tripling or reversing them, and then adding them up to get the thermochemical equation we're interested in. Now, we have to do this in just the right way, so let's see how this method works with this example. Okay, so here's what we have: two given thermochemical equations. Find the delta H for the third. So what we do is we look at our given equations and we see how they compare to the reaction we're interested in. And if we notice, the first one has copper as a reactant and copper oxide as a product, and the reaction we're interested in has copper oxide as a reactant and copper as a product. Then we look at the second given equation. It's got aluminum as a reactant and aluminum oxide as a product. Hey, so does the reaction we're trying to get the delta H for. It has aluminum as a reactant and aluminum oxide as a product. So why don't we just leave that second equation exactly the same? So 2 aluminum plus 3/2 oxygen gas makes aluminum oxide with a delta H of negative 1,676 kilojoules. Let's leave it alone because the aluminum here is a reactant, just exactly what we want. The aluminum oxide is a product, just exactly what we want. It's even got the right stoichiometric coefficient, so we'll leave it alone. Well, how about the first equation, which is in the wrong direction, so to speak? It's the reverse of what we'd like. Well, let's just reverse it then. Let's take this given equation and flip it around and make copper oxide the reactant and copper and oxygen gas the products. Well, if we reverse the reaction, we have to reverse the sign of the delta H value, so we change it from negative 157 kilojoules to positive 157 kilojoules. Well, now we've got copper oxide as a reactant, which we want, copper as a product, which we want, but we need 3 copper oxides and 3 coppers, and we only have 1 in our reversed equation. Well, we can fix that by also tripling that equation. And if we triple it, we have 3 copper oxides makes 3 coppers plus 3/2 O2. But of course, if we triple the reaction, we have to triple the delta H value. So instead of 157 kilojoules, it's 3 times that, 471 kilojoules. And now notice the copper oxide, 3 of them as a reactant, just what we want. 3 coppers as a product, just what we want. So if we take these two reactions that we've now manipulated and add them up, it looks like we're getting the thing we would like, but we also should note that we have 3/2 oxygen gas as a reactant for the first reaction. It's a product, 3/2 oxygen gas, for the second reaction. So when we add these two equations up, they cancel out, and that means that we have now manipulated these two given equations to add up to the reaction of interest perfectly. Now, of course, we're interested in the delta H value, and so if we take these reactions that we've now manipulated and add them up to get the reaction we're interested in, we have to add up the delta H's in exactly the same way. So we're going to take negative 1,676 kilojoules. We're going to add to that positive 471 kilojoules. And that gives us an overall of negative 1,205 kilojoules for the delta H of the reaction that we were interested in. So that's our answer. Now, if we look at this sort of graphically in terms of what's going on or schematically, imagine we look at the enthalpy of our reactants, the 3 copper oxides plus 2 aluminums, and when that makes products of 3 coppers and 1 aluminum oxide, 1,205 kilojoules of energy is given off. It's an exothermic process. The products have a lower enthalpy than the reactants. But we could also think about this process as taking place in 2 steps, where first of all, the copper oxide turns into copper and oxygen, and that requires 471 kilojoules to occur. So the enthalpy at this step is higher for the substances. But then the oxygen reacts with the aluminum to make aluminum oxide, and that step gives off 1,676 kilojoules, and the net amount of energy change for those 2 steps together is the negative 1,205 kilojoules for the direct process. So this is generally applicable because enthalpy is something called a state function. And state functions are things that do not depend upon the path that you take, but they only depend upon where you start and where you end up. And so what we're talking about here is values, of course. The amount of enthalpy change doesn't depend upon the path you take from your reactants to products. It just depends on what are your reactants and what are your products. And perhaps a non-chemistry example would help with this a bit. And another state function is elevation. So imagine you are hiking up Mount Kilimanjaro, trying to get to the summit, and the group you're with is at 5,424 meters, not quite at the summit yet. And some of your group has such bad altitude sickness they can't go on anymore, and they go back down to base camp, which is at 4,219 meters. So their altitude decreased by 1,205 meters for that return to base camp trip. So they have an elevation change of negative 1,205 meters. Now the rest of the group has enough energy and they're not so altitude sick, so they're able to go to the summit, which is at 5,895 meters, highest point in Africa. And after they've reached the summit, of course, they celebrate a little bit, and then they head back home. They've gone up 471 meters from where they started, and then they head back to base camp, and they go down 1,676 meters in elevation to arrive back at base camp with a net elevation change of negative 1,205 meters, same as the group that headed right back to base camp. So these 2 paths had the same net elevation change because elevation is a state function. It just matters where you start and where you end up, not which route you take. So because enthalpy is a state function, we can use something known as Hess's Law, which is that the enthalpy change, delta H, for a reaction is the sum of the enthalpy changes for all of the steps into which the reaction can be divided, even if these aren't steps that really occur. If we can connect the dots from A to B using a series of steps, then if we add up the enthalpy changes for the series of steps, we get the enthalpy change for the overall net process. And there are some rules that we have to follow here. And the rules are that delta H is directly proportional to the amounts of reactants and products. So if we have twice as much stuff reacting, then we have twice as big a delta H. If we have 1/3 as much stuff reacting, we have 1/3 as big a delta H. If we take a reaction and we reverse it, then the sign, positive or negative, of delta H for that reaction will reverse as well. And if we add up reactions to get some overall reaction we're interested in, we have to add up their delta H values in exactly the same way. And if we follow this process, then we can use this thing called Hess's Law to take some known reactions and add them up after the appropriate manipulations to get the delta H for the reaction of interest. The example we did had 2 reactions we manipulated. You might have 3 or 4 in a more complicated example, but the exact same process is followed. And that is it for an introduction to Hess's Law.